everyone, welcome to a video learning about graphing solutions to linear inequalities. So we're going to take the inequality here, y is greater than 2x minus 5, and we're going to look at how to represent that inequality in a graph with both x and y variables. So let's start off by actually inputting some values. We're going to pick some x values, some y values, and find some solutions to this linear inequality. So let's start off by making x equal to 1. So I'm going to go ahead and put that in the inequality. We got y is greater than 2 times 1 for x minus 5. And if I evaluate it, 2 times 1 minus 5 is negative 3. And I can see that if x is 1, y has to be a value greater than negative 3. Well, let's list some of those out. So one solution could be an x value of 1 and a y value of negative 2, since negative 2 is greater than negative 3. Another solution could be 1 and 8, because 8 is greater than negative 3. And another possible solution is 1 and 0, because 0 is greater than negative 3. So there we go, 3 solutions based off putting in a value of 1 for x. Let's do another one. What if x is 3? Let's put 3 in for my x value and see some different solutions we can get back there. So 2 times 3 is 6. 6 minus 5 is going to be 1. So y has to be greater than 1 if x is 3. So that gives us some solutions then of 3 and a value for y greater than 1. Well, 2 is greater than 1. So one solution could be 3 and 2. Another could be 3 and 11. And one more can be 3 and anything greater than 1. Let's just do 3. All right, so we now have 6 different solutions to that linear inequality, the inequality y is greater than 2x minus 5. Well, let's go ahead and graph all these points, these ordered pairs, and just see where these solutions lie. So there's 1, negative 2, there's 1, 0, then there's 1, 8. The first 3 points I found. And we got 3, 2, 3, 11 is way up there, off the graph, and we got 3, 3. Now there's an infinite number of points. We just found 6 of these, right? But at least you kind of get the idea. This inequality has an infinite number of points that we need to be able to find and we want to represent on this graph. So that's the challenge. Is we got y is greater than 2x minus 5. How do we graph all the solutions to this linear inequality? So the first step I want to do is put the whole equation, if I'm dealing with a linear inequality, I want to put it into slope-intercept form. We've already worked a lot with that, but slope-intercept form is y equals mx plus b. And it's nice because then we can easily see the slope. We can easily tell the y-intercept. It's easy to graph. And it'll actually help out a lot when we get into the later part of being able to graph all the solutions to inequality. So this one's already there. It's already in the slope-intercept form, even though it's an inequality, which is really nice. So my slope is 2, and my y-intercept is negative 5. All right, now for step 2. So I've got it in a slope-intercept form. Step 2 is to graph the boundary line. I have y is greater than 2x minus 5. Well, it's greater than what? I need to have a point or a base to be greater than, or if we're dealing with a less than inequality, I need to have something to be greater than or less than 2. So just like we did with single variable inequalities, we would make a dot or an open circle and then either graph right or left first. If I'm dealing with a 2 variable linear inequality, I need to first graph the boundary line and then know where to be greater than or less than from the boundary line. So that's step 2. Once we've got it in a slope-intercept form, then we can actually graph the boundary line. We use our slope and we use our y-intercept to do that, or any of our other methods that we would use for graphing lines. So my y-intercept is negative 5, my slope's 2, so it goes over 1 up 2. over another one up 2, and now we've got a good idea of what our line is looking at. Now before I can just draw a solid line through those points, I need to think about my inequality. This is y is greater than 2x minus 5, but it's not equal to. I'm not given a greater than or equal to. And since it's not equal to, I can't graph a solid line. Remember our 4 types of inequalities: greater than, less than, greater than or equal to, or less than or equal to. Well, this one is just greater than, but not equal to. So I have to take that into account when I'm graphing my boundary line. So let's go think back a little bit. When we did single variable graphs, if it was greater than or equal to, we would make a solid dot. In this case of graphing a boundary line, if it's equal to, I can go ahead and make a solid line. But if I have an inequality that is not equal to, if it's just greater than or less than, then I need to do a dashed line. Just like we would do an open circle with a single variable graph, I need to do a dashed line indicating here's the boundary, but it's not actual part of the solution set. Okay, so this one is y is greater than 2x minus 5, so we're going to do a dashed line. So I'm going to go through and freehanding this, so I'm going to do my best dashed line following the trend there. You can kind of get the idea. But it's dashed, so there's my boundary line, but it's a dashed line, which means any point on that line is not a solution because y is greater than 2x minus 5. All right, step 1, slope-intercept form. Step 2, graph the boundary line. We need to determine if it's either a solid or a dashed line. We are now on to step 3. Step 3 is I need to shade a side. And what that means is I have my boundary line made. Now I need to determine, well, which side represents all the solutions. It's a greater than or less than. So here's where putting in a slope-intercept form is nice. I have y is greater than 2x minus 5, which means y is greater than that line. So if I think about my y-axis and y values get bigger as I go up the axis. So that helps me know then, if I've got my line made, where are all the y values greater than? Well, it's going to be above the line. So I'm going to shade up, and you can start to see the whole solution set. The whole region is everything on that side of the line, up and kind of to the left in this case, but anything straight up from the line is a solution. There we go. We've just graphed all the possible solutions, and now we can start to think about other points that are solutions and other points that are not solutions. You can see all the ones that we did, the 6 points we found earlier, those are all on the solution set. They're all on the shaded side of the line. Let's take a look at another point right there. That's a value of -8, +4. That's in the solution set. So that would be a solution. I could put -8 in for x and 4 in for y and get a value. There's another point down there. If x is -5 and y is -7, that's in the solution set. They're all in that shaded region representing any point in there is going to make it true. Well, let's take a look at one that is not a solution. So there was a point on the other side of the line. It's got x value of 7 and a y value of -5. And that would be not a solution. It's not according to the graph. Well, let's go ahead and test it out that it's not a solution then. So 7 is an x value, and -5 is a y value. So if I put those in for x and y into the inequality, I should be able to show that it's not a solution. So let's go ahead and do that. Let's test it out down here. So is -5, that's my y value, greater than 2 times the x value, which was 7 minus 5? Well, 2 times 7 is going to be 14. And 14 minus 5 is 9. So is -5 greater than 9? No, that's not a true statement. So since that's not a true statement, that point is not a solution. It does not make the inequality true. Okay, I hope that is a helpful introduction to you guys to graphing all the solutions, and there's an infinite amount of them, of a linear inequality.